Welcome to part 2. In part 1, we built a single attention head from queries, keys, and values. But languages has many relationships happening simultaneously. Subject-verb links, phrase structure, references to earlier words. That is why one attention head is not enough. Let's see what the rest of the paper says. Multi-head attention lets the model run several attention patterns in parallel. Each head can learn a different kind of relationships. In this base transformer paper, they've used h equal to 8. So each multi-head attention block runs 8 attention heads in parallel. Now there are two separate knobs, okay? So one hyperparameter is n equal to 6. So how many times the layer stack is repeated? And h equal to 8 is how many attention views happen inside each multi-head attention block. Its result is not just more attention, it is different views of the same sequence. And the best way to understand is you have token embeddings, and this is happening in each layer. So you have head 1, head 2, head 3, looking at different relationships of the sentence. But the attention block remains same, so you're still looking for a different query and key and value kind on that attention block. And then you do a concat, and then you do a mathematical operations on that. The transformer still has 6 layers of multi-head attention. That doesn't change. It is that within one attention block, you have h equal to 8. It runs 8 attention heads in parallel. So now we come to the applications of attention in our model. Now, I'll walk through this and we'll explain it through a visualization. But essentially, if you remember our previous diagram, the encoder-decoder attention layer. Now, the transformer uses multi-head attention in a few different ways. We had this diagram where we said that it is used on the encoder side as well as on the decoder side as both multi-head self-attention and mask self-attention. Now, in the encoder-decoder attention layers, what happens is the queries come from the previous decoder layer and the memory keys and values come from the output of the encoder. So essentially, the decoder looks at the encoder memory and then uses it. Then, the encoder also contains self-attention layers, where in self-attention layers, all of the keys, values, and queries come from the same place. And like we have already discussed, each position in the encoder can attend to all positions in the previous layers of the encoder. And lastly, self-attention layers in the decoder allow each position in the decoder to attend to all positions in the decoder up to and including that position. The key thing here is, since attention block can see all of these words, we implement this inside of scale dot product attention by masking out all values in the input of the softmax which correspond to illegal connections, which we will talk about. So the first part is encoding the input. So we go back to our examples where we are translating from English to French. So we have I love cats, and this is the first encoder layer where it's creating 3 different vectors for encoding. Then you have the decoder state. So in decoder state, you can see there is a query, which is from the output so far, and then keys, which is also from the output so far, and values from the output so far. And then j'aime and le has already been translated, is there. The rest of the word it hasn't seen is masked. So the future output is blocked. And then in the query encoder, the decoder state then talks to the encoder and essentially looks back to the encoder keys, asking which input tokens matter for the next output. And then finally, based on our vector scale dot product, the decoder pulls a weighted mix from the encoder memory. For this example, the strongest value flow comes from the input token cats. And so the attention weights blend encoder value into the decoder state. And then finally, decoder states predicts the next token. In this case, it's chats. Now let's go on to the next few parts. Position-wise feed-forward networks. Attention lets tokens talk to each other, but feed-forward is a bit different. It works on each position separately. You can think of it as private processing for each token after the token has gathered information through attention. This is also very similar to our conventional knowledge of neural nets. So each layer has a rhythm. Attention mixes information across positions, then feed-forward processing transforms each position. Embeddings and softmax, I'm gonna do a quick one here. So the model does not read words directly. Now, if you go back to our first examples where we have this input embedding and output embedding, what essentially happens is the model does not read words directly. It reads token IDs turned into vectors by an embedding layer, and it still does today in LLMs as well. On the input side, input embeddings turn source token into vectors. On the output side, output embeddings turn previous output tokens into vectors for the decoder. At the very top, the linear layer and the softmax turn the decoder's final vector into probabilities over the. At this point, I think we can go back to our diagram, and it suddenly should start making sense. So you have inputs where you have input embeddings, and then we have the positional encoding. I'll briefly touch on it, but essentially, when you're looking at all of these parallelly, you need some sort of encoding so that the positional data is there. Neural nets don't really understand when you put position 1, 2, 3. So the paper proposes a sinusoidal wave-based positioning, which we'll skip. But then it goes to the multi-head attention. Like we said, 6 attention blocks, 8 attentions parallelly, and then it goes to feed-forward networks. Same for the decoder. The only thing here is when it does the output, it masks the future output and instead asks it to give a probability of the various output probabilities of the next token. So now going back, like we said, so their positional encoding essentially injects some information about the relative or absolute positions of the token in sequence. So essentially positional encoding adds positional information to the token embeddings. So this essentially lets attention-based models understand sequence order. Now, coming to the question, why self-attention? Defection is essentially defending the design. The comparison is not just like why attention feels nicer. The paper is comparing cost, parallelism, and path length. It is essentially trying to say is that attention makes the model more parallel and gives words direct communication paths. So you can see it argues is the path length between long-range dependencies in the network. One key factor affecting the ability to learn such depends the length of the paths forward and backward you would do for traditional neural nets. A self-attention layer connects all positions with a constant number of sequentially executed operations, where a recurrent layer requires O of n sequential operations. In terms of computational complexity, self-attention layers are faster than recurrent layers. Now I'm going to skip over all of these and instead talk about some questions you might have. So now instead of looking at the training, I think our time is better spent by me talking about the questions I had when I first started getting into this. So, FAQ section. So, the first question. We all have heard about context sizes for LLMs. In this paper, the attention works over the tokens currently inside the sequence. The encoder can let every input token look at every other input token. The decoder can look at the output tokens it has already written. And in cross attention, it can look back at the end memory as well. So context size here is basically how many token vectors are in the working set that the attention is allowed to compare against. Modern LLMs call this context window. It is not an infinite memory. It is the number of tokens available to attend to, and the attention gets more expensive as that number grows. Next question. What are the hyperparameters here? There is n equal to 6, which means 6 repeated layers of attention, and then h equal to 8, which means 8 attention heads. There are other knobs as well, like d underscore model equal to 512, which means that every token vector moving to the model is 512 numbers wide. Now, when we say I love or cats become a vector, in the base transformer, that vector has 512 slots. Then there are d underscore ff equal to 2048 is this width of the private feed-forward network after attention. So each token expands from 512 numbers to 2048 numbers, gets processed and comes back down to 512. With the 8 attention heads, each head works on a smaller 64 number view, which is d underscore k or d underscore v equal to 64. Now these are choices made before training. They are not learned from the data. Question 3. What are model weights versus q, k, and v? The model weights are the learned conversion recipes. For attention, those recipes are matrices called w underscore q, w underscore k, and w underscore v. A token vector comes in, and the model multiplies it by these matrices to create 3 temporary vectors for that token in that layer. Remember, query, key, and value. So the w underscore q is learned and stored in the model. That is what allows the query vector to point to the right key. The query vector it produces is temporary and depends on the current token, sentence, layer, and head. Same for all keys and values. The full model also has many other learned weights: embedding table, output projection matrices, feed-forward matrices, and layer normalization parameters, which is what you would have in your typical neural nets as well. Question 4. How does this relate to modern LLMs? Modern LLMs inherit the transformer block idea, especially masked self-attention. The biggest difference is that chat-style LLMs are usually decoder only and trained on huge text to predict the next token. They often do not use the encoder-decoder translation setup from this paper, but the attention machinery is directly in this family tree. We'll talk about more in the next video. Finally, when people say a model has X billion weights, how does that map to this paper? Those billions are the learned numbers across the whole network. Embeddings, attention, projection matrices, feed-forward matrices, output layers, all of the repeated blocks. Then you have the weights for query, keys, and values matrices we saw. They are also very important part of the total, but probably smaller. Bigger models usually have more layers, wider vectors, bigger feed-forward networks, and many more learned numbers. Which brings us to the end. Let me know how did you like it and what I can improve here. Remember to like, subscribe, and share.